As we talk about functions, we also need to talk about the domains of functions. We've talked about domains of functions before. We talked about what do we do if we have a denominator in the domain, or we have a denominator in our function. So when we find domains, we're always going to ask ourselves, what can x be? Can it be all real numbers? That would be really nice if it could. If it can't be all real numbers, can it be all real numbers except maybe one or two, maybe three or four specific values? For example, all real numbers except x cannot be 2 and x cannot be -3. Or could it be an interval of values? We haven't looked at any examples yet where it can be an interval of values. We have, however, looked at how the range can be an interval of values when we looked at the range of quadratic functions. So here's where we're at right now. So we've already talked about how can I determine if it's everything except a few certain values? Well, we determine that by looking for denominators. How can I determine if it's an interval of values? That's when we're going to look at radicals. Notice we've also had some situations where it's all real numbers because we've talked about, well, quadratic equations are all real numbers because there's nothing I can't plug in. For the time being, we'll look at some more as we continue to expand on our knowledge of functions. We'll look at more and other ways to find domain restrictions. But as of right now, we're at a position where it's either all real numbers, or we're looking for exceptions in denominators, or we're looking for range of values and radicals. So before I jump into the radical piece of it, let's just do a little bit review. So make sure you can do these. I want to find the domain of each of the following. Well, in example 1, right away I see I have a denominator. My denominator cannot be 0. So I see that that's factorable. So I can say it's positive 6 times negative 2 is negative 12 and adds to be 4. So I can say my denominator factors to be t plus 6 times t minus 2, which means that my domain for this function is all real numbers except t cannot be -6 and t cannot be 2. If I look and do the same thing for example 2, example 1 was nice because I was able to factor my denominator. If I try to factor this denominator, I see I cannot. A lot of times people try to because they see perfect square and perfect square, but remember we cannot change that into factored form unless it's perfect square minus perfect square. So I'm going to go ahead and say, when does x squared plus 1 equals 0? Well, I see that because there's a squared term but no linear term, I can use square roots to solve this. So I would say, when does x squared equal -1? So it's when x equals plus or minus the square root of -1. But wait a second, I know that that means plus or minus I, and I is an imaginary number. Well, when we talk about domains, we are only talking about our domains across the real number system. So since my only restriction would occur at an imaginary number, I can go ahead for example 2 and say all real numbers. All right, so now let's talk about how radicals work. Now that we've had a little bit of review of domains, let's talk about radicals. So with radicals, so denominators, I can't have zeros because it's not okay to have the 0 on the denominator. Well, what about radicals? Well, if my domain is only supposed to refer to real numbers, look at what happened in example 2. I could not have a negative in my radical. So I'm going to use that idea, and on example 3, I'm going to say, hey, my value under the radical, my 4x minus 1, it has to either be greater than or equal to 0, because if not, I'm no longer in the real number system. Well, that would mean 4x has to be greater than or equal to 1, and x has to be greater than or equal to 1/4. There's my domain restriction. I can't have any x values that are less than 1/4, because if I did, it would make my value under the radical negative and would put me out of the real number system. It would give me imaginary numbers. If I do the same thing for example 4, so I look at this, if this had not been 3x plus 7, had it been x or x squared or x cubed, x to the 4, I mean I could keep going, but there would be no domain restrictions. This piece and this piece alone is what's causing my domain restriction. Notice in example 1, I only looked at the denominator. I didn't care what was going on up on top. In example 2, I only looked at the denominator. I didn't care what the numerator had. Same idea here. I'm only going to look at the radical, and I'm going to say my expression under the radical, that 3x plus 7, has to be greater than or equal to 0, because if it's not, it's an imaginary number. So I'm going to subtract 7 from both sides, and get 3x is greater than or equal to negative 7. I'll divide by 3, and I know that my x values have to be greater than or equal to negative 7/3. As long as they are greater than or equal to negative 7/3, my expression under the radical is positive and I get a real number. If I pick anything less than or equal to negative 7/3, or excuse me, not equal to, just less than negative 7/3, my expression under the radical will be negative and I will get imaginary numbers. Looking at the final two examples. On example 5, notice my radicals under the denominator. Well, before I talk more about example 5, I want to point out that on all these, I could be greater than or equal to 0. Because it's okay to have 0 under a radical, just not negatives. So when I look at example 5, my first instinct is to say, hey, I just have to make sure that 2x squared minus 3 is greater than 0. Or, excuse me, greater than or equal to 0. But because it's in the denominator, this is a special case where, hey, actually, you know what? It can't be greater than or equal to 0. It has to just be greater than 0, because if it's equal to 0, I just broke the rule with no zeros in the denominator. So I'm going to add 3 to both sides. I'm going to divide both sides by 2. And I get x squared is greater than or equal to 3 over, greater than, sorry, just greater than, x squared is greater than 3 over 2. But wait a second. When I take the square root, I have to take both the positive and the negative square root. Well, if I have a negative in front of my square root, isn't that a minus 1 times? And if I multiply both sides of a radical by a negative, doesn't that make my sign flip? So the two answers I'm going to get in this situation is either x is less than the negative square root of 3 over 2, or x is greater than the negative square root of 3 over 2. Again, oh, sorry, that one's supposed to be positive. X is greater than the positive square root of 3 over 2. Because again, I have to remember that when I take the square root, I need plus or minus, and I have to remember that when taking a minus, I have to flip the sign. So either of those regions will make sure that I have real numbers underneath my radical. In the final example, example 6, I have two things to look at. I have both a denominator and a radical. Doesn't matter where you start. Let's say I start with my denominator. So the first thing I say is, hey, x squared minus 9 cannot be 0, which means x squared cannot be 9, which means x cannot be positive 3 or negative 3. Then I look at my radical. And on my radical, I say, well, that means that 8x plus 4 has to be greater than or equal to 0. I'm not in the denominator, so I can be equal to 0 again. Which means 8x has to be greater than or equal to negative 4. And x has to be greater than or equal to negative 4 over 8. 4 over 8 is 1/2. Well, here's the deal. If x has to be greater than or equal to negative 1/2, doesn't that automatically mean it can't be negative 3? I can list all three of these pieces. I can list these two restrictions and these two individual restrictions and this interval restriction. However, by listing that x has to be greater than or equal to negative 1, I'm telling whoever reads that yeah, that means it can't be negative 3 because negative 3 isn't greater than or equal to negative 1. So for my final answer, all I have to do is say x has to be greater than or equal to negative 1/2, and x cannot be 3. If you said x cannot be negative 3 or 3, it is redundant. I will not count you wrong, but no, it is redundant. It's better to just say it has to be greater than or equal to negative 1/2 and cannot be 3. So, to recap domains, check for a denominator. If you have a denominator, the denominator cannot be 0. Check for radicals. Radicals, the expression inside of the radical has to be greater than or equal to 0. Unless the radical's in the bottom, then the expression has to be greater than 0.